Hi everyone, welcome back. As I mentioned in the last video, we're going to Python and we're going to see another cobwebbing demo, this time of this particular x sub t plus 1 is equal to r minus x squared. And we're going to talk about both periodic solutions as well as we're going to talk about the periodic solutions as well as the what we did previously in terms of equilibria. So now, in order to do that, we're going to go ahead and get started. So if you recall from one of our lectures a couple weeks ago, we're going to get started by importing matplotlib. And let's say that we're going to import numpy as np because we like that. So we're going to find some function, f of x, and this time our function is just going to be 1 minus x squared. So 1 minus x times x. And you can set your axes, so subplots. And I'm going to set our limit to be -2 and 2, as well as for both the x and y axes, just because will make it a little bit easier to see the behavior that's going to happen here. And of course, you should always label your axes. So set x label, set x label. That's going to be the x-axis. And set y label is going to be the y-axis. And I'm going to go ahead and set aspect to be equal and a box. Because otherwise, matplot doesn't always plot the x and y axis as having equal length units, which is a little bit irritating. And then the next thing I'm going to do is I'm going to plot. I'm going to say mp.arange, let's do this to 100, 10 minus 5, and mp.arange, let's say 100, 10 minus 5. This is going to be our y equals the x line. And basically what I'm doing here is, let me actually show you in a little bit more detail, mp.arange of 100 is 0 through 99. If I divide that by 10, that's going to be 0 through 9.9. And if I subtract 5, that's going to be -5 to basically 5. And so I'm plotting, and then I'm doing that for both the x coordinate and the y coordinate. So that just gives us the y equals the x line. Let's see. Let me see if I can actually make that green to match what we were doing in the text. Ah, yes. So now that's green. Okay, and let's remove that. So as you can see, we now have a green line, y equals x line. And of course, you also want to plot out the function line. So it's mp.arange. I'm going to just have go from -5 to 5, even though we're only looking in -2 to 2, just so that if I zoom out or zoom back in, we can see a little bit more. And then of course, we need to apply this function. F of x is equal to 4x in mp.arange 100 and divided by 10 minus 5. Okay. Yeah, actually, let me go ahead and write this in a slightly nicer way. So let's say plot points is going to be equal to mp.arange 100 divided by 10 minus 5. And so let's set this variable, and let's call these plot points. Oh, well, I didn't want to leave the color green. So this way we can change that later without having to change it manually by hand for each of these. Oh, I think I have an extra parentheses for x and plot points. There. Okay. So now let's keep on going. I'm going to set the number of iterations, so this is going to be equal to the number of times that I'm doing the cobwebbing. Let's set that equal to 10. And let's say I'm going to start at 0 for now. We'll see later that this actually might not be the best choice, but let's start with 0 for now, since it's a very nice, easy place to start. And I'm going to do the same thing I did last time. I'm going to have some list of points, and I'm going to append x0, 0 as the first point. So this is 0, 0. That's where I'm going to start my cobwebbing before going up to the y equals f of x line. Well, actually, I should show you the y equal f of x line as well. What color did I do y equals f of x? I did that in purple, so let's set that in purple. Let's see, what happened here? I clearly just did something wrong. So I plotted plot points, f of x for fx in plot points, and I set my color equal to purple. Maybe purple isn't a valid color. Here it is. I forgot to actually return my value. Return 1 minus x squared. Let's try that again. There it is. Okay, and let's set the color equal to purple. Okay, so now we have that, and you could draw it by hand and do the cobwebbing that way, but we want to do it by a computer, so we're going to start by appending a bunch of points to a list. And so, what's our iteration? For I in range iteration, we're going to take x, y is equal to the last point in the list, so that's minus 1. Y is equal to f of x, and then we're going to append that point. So this is going up to the up or down to the f of x line. And then we're going to go left or right back to our function. So x is equal to y, and we're going to append that as well. And we're going to keep on doing this for a while. And then we can show you what this point list looks like. This point looks, that's actually sort of interesting. It goes 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. Now, you might wonder why that is. Well, if you recall, we probably should have documented this to begin with. Actually, let me put this up at the very top. So if you add together a text section, so what are we cobwebbing here? So you can use Markdown in the Google Colab or a Jupyter Notebook. So this is often ideal. So we are going to be cobwebbing a periodic solution of the function, cobwebbing a periodic nonlinear solution. Okay, and so our function is going to be, let's see, what was our function? It was x sub p plus 1 is equal to r minus x squared. Difference equation is 4, and then we set r equal to 0. Wait, no. We set r equal to 1. Yeah. For r equal to 1. 0 is not so interesting. I know I mentioned 0 in the previous case, but it's a little bit less interesting, so let's set r equal to 1 instead. And so that's why we have this 1 minus x squared down here. Okay, and well, so that's what we're doing. But recall that the periodic solutions. So periodic 2 cycle is given by bar x sub 1 comma 2 is equal to 0 or 1. And that's exactly what we're seeing here. You see it goes between 0 and 1 and back and forth again. And let's actually plot that out so we can see that a little bit more visually. So let's see what's going on. Well, we need to reshape this. So I'm just going to use MP array of this point list. And then I'm going to take the transpose and take the separate x and y coordinates. And then we can plot this. And what happens? So we started here at 0, and then you go up, and you go to the right, you go down, you go, and so it keeps on going back and forth. And so you can sort of see already that this is a periodic solution. Let's actually see that a little bit more nicely. So I'm going to do something, let's start at a slightly different point and see what happens. So if we start at the point 0.1 instead, oh, interesting. So it goes up, and then it seems to go back out to that cycle. So it limits to that cycle. We'll be studying these more explicitly a little bit later. Actually, let's make this all a little bit bigger, just so that it's a little bit easier to see. So let's set the size of our thing. So where was the figure? Let's set the figure size. Size inches to 1010. Okay, so you can sort of see what's going on. You're starting here, you go around, and then you limit to the cycle. What happens if I start at, let's say, 0.5? Yeah, so you see this sort of cobwebbing behavior. I am going to do something to make this a little bit easier to see. I'm going to animate this. So this is a little bit fancy, but I'm going to give you all the code for it. This will work if you're in a Jupyter notebook. It's a little harder to do if you're working on the command line or well, if you're not working in Jupyter notebook, because the animation won't show up properly. But you still can't animate it. I'm going to do it here. So we're going to import animation and RC, and from ipython.display, we're going to import HTML. Okay, so now we've done that. Animating it is a little bit of a pain, but it's not so bad. Instead of just plotting it here, what we're instead going to say is we're going to set an arbitrary line that's going to be equal to this plot. And if you were to just do this, it would just show the entire thing again. And instead, what we're going to do is we're going to define an update step, number x, y, line. And this update step is going to only take the line up to a certain number of iterations. So let's say x num, y, everything up to whatever the current iteration number is. And then we're going to return this line. And we're going to define animation, anim.animation to be func animation of the figure, so that's what we're updating. We're going to use our update function, and the total number of updates is going to be the length of x, or also num iteration. And we're going to be passing some arguments to the function, x, y, and line. Since those are our three things we're passing there, it implicitly passes the number to it. And let's say our interval is equal to 500, so that's how long it takes between the animation steps. And let's see, interval equal 500, so it can be lit equal to true. This is a bit fancy. I don't expect you to be able to do this. And we're going to do an animation to an animation. And then what happens? Okay, let's see. I actually made this a little bit too big, so you can't see it anymore. Let's make this a little bit smaller. Let's say, where was it? Let's make that 6 by 6. Let's try that. Okay, so that's a little bit nicer. So now, if you hit the play button, you'll see it going. Okay, and you can see it doing some number of iterations. Let's actually do a couple more iterations just so we can see what it does as you go further. So we need to run that. And let's try that again. Okay, so you see that it is cobwebbing, and this is where the name cobwebbing comes from, because you get this nice spider web-like behavior. And you'll see that even if you start at 0.5, you start getting closer and closer to the 0, 1, 2 cycle. And if we do this many more times, let's say 50 times, then you notice that it gets closer and closer to the 0, 1 cycle that we know exists, but doesn't ever actually get past it. And so you can sort of take this to interpret it as it's limiting to that cycle. And so you might conclude from this sort of animation that the 0, 1 cycle is asymptotically stable, which it happens to be. So this is a little bit heuristic. Let's start somewhere else and see what happens. So if we start at, say, minus 0.5, well, we're pretty far away, so this might not work anymore. But we'll see. So we're starting at minus 0.5. Oh, no, it still works when you're a little bit further away. I actually forget if this is globally stable or not. So this is one way of seeing it. So this is cobwebbing by ordinary cobwebbing. Let's give this a name. So this is ordinary cobwebbing with a y equal x and y equal f of x. Now let's duplicate that and do again, let's do cobwebbing of y equal x and y equal f of x, and see what happens there. So let's create, so we actually need to copy all of our code here. You don't need to copy all of it necessarily, since Jupyter Notebooks retain state, but I'm just going to copy all of it so that we make sure we get everything. And instead of doing this 1 minus x squared function, I'm going to define this to be f0, and we're going to instead cobweb f of x, which is going to be return f of x. And let's see what happens now. Oh, what did I do? Maximum recursion to, sorry, this needs to be f0 of x, because that's what I named it. And now instead, this is the function f of x. So that's the plot of that function. And now if we start at minus 0.5, we'll see what happens. So you'll note that it seems to be getting closer and closer to this zero, the 0 point. And so you know that 0 is, which is the 0 of our 2 cycle, but here instead of plotting it for f of x, it's f of x, it limits to that instead. And so by plotting f of x, you can instead just use cobwebbing in the normal way and look at the equilibria points, which are of course just the intersections of, which of course are just the intersections of the y equal x line and the y equals f of x line. Okay, and let's start somewhere else. Let's start at 0.5 and see what happens. If we start at 0.5, well, we start there, and again, we limit to the same thing. What happens if we start at 1.5? Let's see what happens there. So we start there, and you jump around, and you do actually end up limiting to the same thing there, which is a little bit nice. But yeah, so as you can see, there are a couple different ways you can use cobwebbing using to actually see the behavior of these solutions. Either you can do it via seeing a limit to the 2 cycle layer, or you can do it by plotting f of x, and then if you know it's a 2 periodic cycle. So if you don't know that the period is 2, then you might just do this instead and see like the overall behavior. And there are ways of seeing this with systems of first-order equations as well. But cobwebbing is a nice intro to these sorts of graphical tools that you can use to understand the stability behavior of nonlinear difference equations. I think that's about it, and so I will see you in class.